Welcome, engineers, to 1.1.1, Part B, which is entitled Inclined Planes, Wedges, and Screws. We're going to talk about the other three simple machines: mechanical advantage, ideal mechanical advantage, actual mechanical advantage, efficiency of these three. So remember, am I free? The actual mechanical advantage, the force divided by the force. The ideal I'm a deer. Ideal mechanical advantage is distance. So the other three: inclined plane, wedge, and screw. This inclined plane has got a roller coaster. You've got a wedge, a fireman's axe, and a screw. And we're going to talk about each of these in turn today. Remember, mechanical advantage. If you have a mechanical advantage of 4, that means that, like, if this thing was 100 pounds, then I'm only having to push 25. So it's 4 times less. But you got to go 4 times more distance. So if it's a force multiplier, you got to pay for it with distance. And in reality, if this is 25 pounds, I'm probably going to have to push more because of friction. It's in a way, it's a lot like a loan. Like in a house, it's like, man, I could just buy this $300,000 house if I had $300,000 in my bank account, or I could get a loan from a bank and you pay a little bit in interest, so I could pay like $1,500 a month, over time. But then you end up paying more because, I mean, for $300,000 house, you end up probably paying like $600,000 to $500,000 over time. It's insane. It's criminal, man. Interest, banks, they've got you. How nice it would be if we were just rich, or knew somebody rich. If you've got a mechanical advantage bigger than 1, that means it's a force multiplier. You put in 5 pounds, you get out 1 billion. If you have a mechanical advantage less than 1, that means that it's a distance multiplier. I push a little bit and that thing really goes, but you always pay for it by pushing with more force or more distance, depending upon which one you've got. I'm a deer, remember? Am I free? We talked about that a couple of times in the last 2 videos. Inclined planes. It's when you're pushing something up a flat surface. We've probably all gone up an inclined plane just driving our car up a ramp. I think most driveways, all sorts of stuff. When you move, you use like a dolly. You go up a ramp. With an inclined plane, the distance that you exert. So if here's my effort, the distance that I'm doing it is up the incline right here. So that's the distance of effort, and the distance of resistance is the height. So when you do this, sometimes I just say it's dE over dr. The distance of our effort is the hypotenuse, and the resistance is just lifting it straight up. So in this one right here, what's the ideal mechanical advantage of this one right here? 15 feet divided by 4 feet. 15 divided by 4, boop, 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 3.75. Or 3.8, using significant figures. So that's ideally what it should be. Now, actual mechanical advantage. So the actual mechanical advantage, it's the force of resistance, and that one sometimes confuses me. When I look, I see 20. And I see 50 for the forces. Which one goes for the FR? What's easier for me a lot of times is the force of exertion, the force of the effort. Oh, I know that one's 20. And through process of elimination, if I know the effort force is 20 pounds, that means that the resistance force is 50 pounds. So 20 divided by 50 is 2.5. Again, it should be 3.75 because that's what we calculated in the problem right before it. Like, it should be 3.75, but it's actually 2 because of friction. So now you can calculate your efficiency. How efficient is this? And if you remember the last couple ones, they were in the 80s, like 80%-ish was a pretty good number. So let's see here. The efficiency is actual divided by ideal. So the actual mechanical advantage is 2.5. The ideal mechanical advantage was 3.75. So to do that, I need my calculator. It's going to be 66.6 or 67%. Pretty bad in the ones that we've done so far. The ones we've done so far in our example problems have been in the 80s. This one's in the 60s. Not a big deal. Just turns out that 33% of everything you put in goes to heat or sound or some other stretching. A wedge is something that when you push, it diverts the force outward to split and open something or lift something. Oh man, you can lift houses. I lifted my house when I finished my basement. There was a support post. I took a wedge and I put in a pole right in the middle of my house, and I pounded that son of a gun in with a sledgehammer, and I lifted my entire house 1/8 of an inch just so I could pull that pole out. It was pretty impressive what you can do with some of these machines in just one human being. In a wedge, the DE over the DR, the distance of your effort. When you take a wedge, you're driving that wedge in. So here's the effort force, right? You're driving the wedge into something. And then what happens is it's opening it up, and that's the resistance. So in this case, the effort force is 10. It's the long one. I mean, again, your wedge can be different shapes, so it's not necessarily always the longest one, but when you drive your wedge in, when you pound it, that's the distance of your effort right there. So this ideal mechanical advantage right here is going to be 10 divided by 3, which is going to be 3.3 repeating, or 3.3. So this ideal mechanical advantage, 3.3. Now they're actually going to give you some forces now. So the effort force, again, it's sometimes hard for me to identify which one is the resistant one. Is it 700? Is it 250? But I know in a wedge, when I hit it with the hammer, I'm pushing with 250 pounds. So the effort force is 250 pounds. And then by process of elimination, that means that this is 700. So 70 divided by 25, that's like 20 over 25. 20 over 25 is 4/5, 2.8. So it actually is 2.8. If you can remember, it was ideally supposed to be 3.3, so it's supposed to be 3.3, but it's actually 2.8, and that makes sense because that would be your efficiency. So your efficiency is going to be your actual divided by your ideal. So your actual mechanical advantage, 2.8. Your ideal mechanical advantage, 3.3. So using my calculator again, that one I can't do in my head. 85%. Again, not bad. Seems like it's pretty much on par with all the other machines that we've seen so far. If this is true to life, I don't know if it is or not. Maybe they're just making these numbers up. A screw. There are some purists out here when it comes to simple machines. Some people think that there's only 3. And they say the screw is a combination of an inclined plane with a wedge, an inclined plane with, let me think, because they say that the 3 are an inclined plane, because they say an inclined plane is a wedge, so they can get rid of them there. And then a wheel and axle is the same thing as a lever. In a way, if you think about it, they're kind of just levers. So some people say only inclined plane, only lever, and only pulley. So this would be like an inclined plane with a wheel and axle, in other words. So, boop. Some properties, you can take rotary motion, turning something to move it forward. Like if you've got a linear bearing, like some of you have maybe used a 3D printer or CNC machine or CNC router or CNC plasma. they're taking a stepper motor to move these very, very fine movements so you can get really high detail depending upon what's called your pitch and the resolution of your stepper motor. How small of an increment can it turn? A screw, screws have all sorts of cool stuff, and you won't understand it until you need to go to the hardware store and get yourself a screw. Some of you have gone into the hardware store. I used to work there, and I learned very quickly that there's probably 1,000 different types of screws, and they're all identified by a lot of different stuff. So this one right here is a half 13 NC. These all have different things. The 1/2 is the diameter. Now, I believe it's the diameter from the outside to the outside, not the in, you know what I mean, like the base of these threads. So the outside to the outside. 13 is the number of threads per inch. So if you were going to label out 1 inch, this would be 1 inch. There would be 13 of these threads. If you counted each of these things, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. There's 13 of those little threads per inch. A really common one, it'd be a 1/4 20. So it'd be a 1/4 inch in diameter, and there's 20 threads per inch. So you can sort of see from these two numbers how like different numbers would correspond. Oh, that would be a really thick bolt. Oh, that'd be a really skinny one. Oh, that'd have really fine threads. That would have really big threads. The NC, I don't exactly know how different types of threads. I do know that if you have, there's one called NPT, which is a pipe thread, and that would mean that this screw would actually taper. So instead of it being straight, your bolt would look like this. So as you screwed the thing in, it would get tighter inside of the tube. We would use that for plumbing and gas. So like when you go to turn something in, you want that to be an airtight seal. All your gas lines at your house, if you have natural gas, which many people do, they're NPT threaded, just so when you screw them together, they get tighter and you don't have gas leaks and it doesn't kill people. It says how far will a screw with 13 threads per inch move linearly if you turn it 1 rotation? Ah, that's clever. So if we turn this bolt right here in this picture, if we turned this bolt around once, if you spun it around once, it's going to go 1/13 of an inch. 1/13 of an inch. And you can tell that maybe if you turned it half of a way. If you turn this thing only around half of a screw, it would be 1/26. And if you did a 1/4, it would be like 1/54. So you can see very quickly that this is a way to really finely control things. If you need to move something very, very small amounts, using a screw to do that is really a clever way to change rotational motion into linear motion. In a screw, the distance that we exert, it depends on your wrench. Like if you put a wrench on a screw and you turn it all the way around once, it's the circumference that your hand moves. So your hand is going to move a really far distance. Like let's say you put a 1-foot wrench on this thing. Here's your wrench, and if it's 1 foot, it's gonna go a really far distance. That's like 2 pi r, so it's gonna be 2 times pi times radius. So that's gonna be 6 feet. Like that's gonna go a long ways, right? And this thing's only gonna go up 1/13 of an inch. So like, not 6 feet, it's going to go 72 inches, and this is going to go up 1/13. So the mechanical advantage here is huge. It's absolutely gargantuan when in the world of simple machines. So this can get a little complicated depending upon what you're using. So distance of the effort, 1 rotation. Distance of the resistance is 1 pitch, 1 thread. So here you go. What is the ideal mechanical advantage of the screw above if you use an 8-inch long wrench? And here we're actually going to do it. Son of a gun. So we've got this wrench, and it's 8 inches. So it's going to go around it. So it's going to be okay. So ideal mechanical advantage. I'm a deer. The distance that I exert, it's a circumference. So it's 2 pi r. The distance of my resistance, this is a 1/4-20. So this is 1/20th. Because if I go all the way around once, it goes up 1 thread. So that's going to be 1/20. Or if you want to, it's 1/10. So 0.05 if you really wanted to put it as a decimal. So I'm going to roll in my calculator. I'm going to take 16 pi, which is 50.3. And then 1/20, I said before, was 0.05. And I'm going to divide those things. Or, if you're really good at math, it's kind of fun. The 20, since it's in the denominator, it's going to come up to the top. I'm not saying good at math, but it's a clever little trick. So basically, it's 50 times 20. 50 times 20 is going to be like 1,000. 5 times 2 is 10. 10. Yeah, I think 1,000. Yeah, that's right. Yeah, 1,005. Oh, dang. Significant figures. So I'm going to go 1.0 times 10 to the 2. 3. If you don't understand significant figures, you have to use as many as there are in this has I mean, I can only use 2 significant figures basically because this has 2 in it, so my answer can only have 2. So 1,000. So this has an ideal mechanical advantage, kids, of 1,000. Like, this is huge. Way, 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 way bigger than what we're normally used to seeing. And now they actually give you some forces. So you're exerting a force of 35 pounds on the wrench, but then this exerts a clamping force of 1,200. So we can find the actual mechanical advantage. So actual mechanical advantage, the force of resistance. Again, hard for me to understand, but the force that I'm exerting, I totally know that's 35. So I'm putting 35 pounds on the wrench. This thing, the resistance is 1,200. So 1,200 divided by 35 is equal to 34. That's a far cry from the 1,000 that it's supposed to have. This efficiency is totally in the toilet. Totally in the toilet. So let's see. What is the efficiency? It's the actual mechanical advantage divided by the ideal mechanical advantage. So 34 divided by 1,000. So 34 divided by 1,000, I can do that. It's 34 thousandths. Oh, that's 34 hundredths. So it's going to be 0.034. And I'm going to use my calculator just to do it. Just to satisfy myself. I mean, duh. Yes, of course it is. And then in percentage-wise, that's 3.4%. Really, really bad. This is the semi-truck of the simple machine world. It doesn't get good fuel economy. Most semi-trucks out there, kids, they get 5 miles per gallon. It's really bad, but they can move entire houses. This thing, 97% of your energy goes to heat and friction, but you can exert huge forces. I mean, entire skyscrapers are held together by these things right here. I mean, the biggest, yes, really, really neat. So, thanks again for watching. Well, compound machines, again, just multiplying them together like we did before. But thanks for watching. incline planes, screws, and what was our other one? Wedges. That's right. Have a nice day.